All right, this is the fundamental forces and atoms video. So the original question is, well, what are the fundamental forces of the universe? So we look at the four fundamental forces, and they explain every interaction experienced every second of every day. So for all four forces, you're going to learn how strong it is, how far it reaches, how it affects your life, and what makes it special. So the first thing that I would have you do is the fundamental forces challenge. So the challenge of this task is to rank the fundamental forces from strongest to weakest. So you just make a list 1 through 4, and you list them from strongest to weakest. So these are the four fundamental forces of the universe. So you've got electromagnetism, the weak force, strong force, and gravity. So if you just you can pause it there. You can make a list and try to rank them. And this is how I score it, just so it's out of 10 points. So we'll just go strongest to weakest. So the strong force is going to be the strong force. So the strong force holds the nucleus of an atom together. It is the strongest force. Now the range is about the width of the nucleus of an atom. So you can see in that diagram, it doesn't really reach beyond the nucleus of an atom. So the next strongest force is going to be the electromagnetic force. So the electromagnetic force is the attraction or repulsion between positive and negative particles. It's the only force that repels, and its range is infinite. So you can see here that similar charges repel each other and opposite charges attract to each other. Now, the weak force is the strongest, or the third strongest force. The weak force is responsible for radioactive decay. It has the shortest range of any force. So its range is about the tenth the width of a proton. So if you zoom in on that atom, you can see here just the tenth the width of an atom, right? So it's not that much, and it is responsible for radioactive decay. Now, gravity is going to be the weakest force, right? So if we compare, if we make the strong force with the strength of 1, which is the strongest force, gravity would have a strength of 0 point followed by 38 zeros, then a 6. So that number right there. Right now, gravity is the attraction of all mass, and it is the weakest force, and its range is infinite. So this is a nice little chart that'll help us keep track. So we compare the strength of all the forces to the strong force, which we just say has a strength of 1. So everything else is going to have strength less than that. So you can see here the electromagnetic force 0.07, so relatively weak compared to the strong force, and the weak force 0.000001, and then gravity is in last, and it has the it's the weakest of all forces. All right, so the question is, if gravity is the weakest force, why does gravity hold you to the earth? So if we look at somebody standing on earth, right? So the strong or the weak force, why doesn't it hold you on the earth? Well, the answer is because, like, the range, right? I say, hint, look at the ranges. The strong and the weak force don't really leave the nucleus of an atom. So we don't really interact with it on a macro level, like us just walking around. So why does the electromagnetic force pull you to the ground? Well, I'm going to tell you something right now, though. It does. There is an attraction of you to the earth, an electromagnetic attraction, because you are made of protons, you are made out of electrons, so is the earth, and there is an attraction. But remember, the electromagnetic force is the only force that can repel. So yeah, you do have protons, electrons in your body. Same thing with the earth. Well, those opposite forces attract, but those similar forces repel. So since we're made, there's about the same number of protons and electrons, they sort of balance each other out like this. And gravity only is only pulling, it's only attraction, because, and that's why, even though it's such a weak force, it only attracts. That's why gravity is what holds us to the ground. So this is the standard model of the universe. You can see here it's made out of 17 particles, and some particles have to like there are particles that like carry the information to those forces. So gluons carry the strong force, photons carry the electromagnetic force. So that's photons, like in light, and photons are just ripples in the electromagnetic spectrum, and that's how we interact with them. We see them. W and Z bosons carry the weak force, and then gravity is that odd one out, right? So gravity is the odd one out where we haven't really discovered gravitons. We don't really know what gravity is right now. Like we know, like we can see that it's like the bending of the curvature of space and time, but gravity is still kind of a mystery. So here's another question, though. Can you ever really touch anything? So just think about like two magnets being pushed together, right? There is a repulsion, right? If you have the similar sides facing each other, they are going to repel each other, right? So if we look at the same thing, if we zoom in on atoms, it's the same thing with atoms. Now, atoms on the outside have electrons, and those electrons are similar charges, and they're going to repel away from each other. And the closer those atoms get together, the more that repulsive force pushes. And you can see here it's an inverse square law. You can see here the closer they get, gets much stronger. Now, if you look at the equation for the force of an electromagnetic force right there, um, could you ever really touch? The radius, could the distance between those two atoms ever be zero? And the answer is no, because then you divide by zero. So what happens is right before that they would touch, that strength would be infinite, repelling each other. So touch is just a word that we as humans use to describe objects getting really close, but nothing can ever really touch anything else. Right now, no, it's like feeling cold. It's just a way that we use to describe how we interact with the universe, right? Or something is rough, right? Like like atoms and molecules don't have the property of rough or cold. Or like the question is, is water wet? Like that's just our brain, how it processes how it feels. Water molecules don't have the property of being wet. It's just how we interact with the universe. So that's the same thing with touch, right? So we're not actually touching anything. Our brain just interact. Our brain can just, our neurons interact with that electromagnetic repulsion. It can feel that. So here's another question to ask ourselves: which of the fundamental forces has the largest impact on our lives? And to answer this, we did the fundamental forces activity, right? So you can, we know about the fundamental forces, and in all of these, I give you 10 different scenarios, and in all these scenarios, you're supposed to be able to tell like what force is what force is responsible for them. So these are the all of the different scenarios. Now I'm gonna, if you want to, you can pause and you can try to take a guess. You can look back and see those different forces. But let's just take a look at all of these one by one, right? So so I'll give you time if you want to. You can do that. But the big question at the very end: which of the fundamental forces has the largest impact on your life, and explain why? Okay, so let's just take a look at these one by one. So getting punched in the face, right? Kind of a funny thing, whatever. But what happens is that the electrons in that fist are getting close to your face. The electrons in your face. Now they're going to repel each other. Now your neurons definitely react to that electromagnetic repulsion, but it's going to be the electromagnetic force is responsible for that because it's those atoms getting closer together. Same thing with a car hitting a tree. So a car hitting a tree, the electrons in the car are getting close to the electrons in the tree, and they repel each other. Falling after jumping off from a diving board. So this is going to be gravity. Gravity is the attraction of all mass. That's what gravity is doing. It's pulling you down. Photons hitting your eye as you watch a movie. So as we've learned, the photons are what carry the electromagnetic force. So like they're just ripples in the electromagnetic field. That's what that's it's the electromagnetic force is responsible for you being able to see things. Air vibrating as you're listening to music, and you see here there is a simulation that can let you see. But all sound is the like waves in the air, and it's just those molecules getting close to each other and repelling, and it's just a wave. So that is the electromagnetic force. Car coming to stop after slamming on the brakes. So this is friction, but friction, all that is if you really zoom in, it's this electromagnetic repulsion. So that's going to be the electromagnetic force. Pushing off water while swimming in the pool. Same thing. Your hand is repelling those water molecules because of the electromagnetic force. Those electrons are repelling each other. Proton being turned into a neutron in a banana after some potassium goes through radioactive decay. Well, this is going to be the weak force. Remember, weak force is responsible for radioactive decay, using electrical impulses in your brain to think. So this is the electromagnetic force. So your brain is just organized to send the electromagnetic pulses throughout it. It's it's in a different pattern, but it is the electromagnetic force. Nucleons being held together in the nucleus of an atom. That's what the strong force does. The strong force holds the nucleus of an atom together. Now that final question, which of the fundamental forces has the largest impact on your life? Well, if we look at all of these, like the majority of them are going to be the electromagnetic force. Now, it doesn't mean any of one is more important or less important. They're all important, but everything you touch, everything you see, everything you think, everything that you basically are is because of the electromagnetic force. Now, gravity, yes, it is important, but all that really does is it holds us down to Earth. Yeah, the electromagnetic or the strong interaction or that strong force, it holds the nucleus of atoms together. Yes, it's important, but we really don't feel it on the macro scale because it doesn't get outside of the nucleus. Same thing with the weak interaction. Yes, it's important for radioactive decay, but we don't really experience it because it doesn't really leave the atom. All right, so now here's another challenge that you can do, the Atomos challenge. So the challenge of this task is to cut a group, to be the group that can cut like a strip of paper. So you just get a little strip of paper, 8 by 11. You don't have to, you can make just a little strip that's, 11 inches long. Cut that strip of paper in half as many times as you can. There you go. All right. So this is just an idea to we're really thinking about the fundament, like the atom, right? And we'll get to what atomos means. But if you were to cut that piece of paper in half, you can see here you'd have to cut it in half 31 times to be about the size of an atom. So that's just a way to think about how many times do you have to do that. And it gets really tricky because normally I think the average is 9 to maybe 11 um, cuts, right? And then you still got to keep cutting into half over and over again till you get to 31 cuts, where you're at about the size of an atom. So here's some history about the atom. So Democritus first proposed the idea of atomos in the year around like 400 BC. Now, atomos is like Greek for uncuttable, right? So the idea is that there's this fundamental, you can cut something in half so many times and eventually it reaches a point where it just cannot be cut in half anymore. All right, so he proposed that atoms were infinite number, uncreated, and eternal, and that the qualities of an object result from that kind of atoms that it's made out of. All right, so then we fast forward about 2,000 years and we get to John Dalton in the year 1803. So he introduced the sphere model of the atom. So he proposed that atoms of different elements have different properties like mass. He also proposed that atoms rearrange during chemical reactions. So this is kind of a big deal in 1803. And in fact, John Dalton did a lot of experiments and he identified several different atoms. I think it was maybe 15 to 18. But it's a big deal because this is in 1803, and the periodic table wasn't around until about the mid to late 1600s. That wasn't started. So just looking at the properties and so now we're starting to understand. Okay, well, what is this fundamental particle that everything is made out of? So then we fast forward a little over 100 years. J.J. Thomson discovered the electron. So he introduced the plum pudding model in 1904, in which he proposed that matter was made of positively charged pudding with negatively charged electrons distributed throughout. So he was able to isolate the electron. He said, okay, something's coming off of these atoms. I know it's negatively charged. And so he said, okay, well, maybe like things are just made of this, called it plum pudding, right? This amorphous blob thing, and electrons, these negatively charged electrons are scattered out, and you can isolate them. That's what he thought. Now, so then let's talk about actually being able to observe atoms without really being able to observe them. That brings us to Albert Einstein. Now, he didn't propose a new atomic model, but he was instrumental in understanding atoms. So he used what is known as Brownian motion to measure how big atoms were. So atoms are small, but it's a big deal that he was able to do this. So Brownian motion. So in 1827, while examining grains of pollen of the plant suspended in water under a microscope, this botanist named Brown, he observed minute particles ejecting from pollen grains, executing like a continuous jittery motion. So they were constantly moving, just like you can see in that graphic off to the right. He observed the same motion particles of inorganic matter, enabling him to rule out the hypothesis that the effect was life-rated. So it was just, he was able to see that there was just sort of this random motion to small particles, right? So if you put food coloring in water, you can kind of see this, right? There's really, why does the food coloring, if you don't mix it up, why does it randomly sort of disperse about? And eventually, if you come back several minutes later, you would notice that it is fully distributed out. So that's like Brownian motion. It's kind of a big deal. And Einstein came along and he was able to measure about how big molecules were. This is sort of like the first conclusive proof that atoms existed. So now let's get to Ernest Rutherford. Now, Ernest Rutherford discovered the proton, and he introduced the nuclear model in 1911, in which he proposed that the positively charged particles were located at the center of the atom. He did this with this famous gold foil experiment. So there are simulations that you can see this. So this was the idea of this. Now, here's what the goal. So let's answer this question. How did Rutherford do this? How can we see something too small to see, just like Rutherford did? So this is the gold foil experiment. So essentially what he did was he aimed like these alpha particles, which are just basically helium nuclei without any protons. Right? They were radioactive, radioactivity was being explored at this time, and he aimed it at this thin strip of gold foil. Now he said, okay, well, if Thomson's model is accurate, then all these alpha rays should just go right through, right? There's really nothing for it to bounce off of. These electrons are really tiny. It's not really going to affect it. Everything should just go through. But that's not what happened. Some of them were deflected, and some of them were like reflected back. Some of them bounced off. So this is what he discovered. These positively charged alpha ray particles were bouncing back or getting deflected, but most of them went through. So this was a lab to recreate Rutherford's gold foil experiment. You can watch that video there. But this is an experiment in which it sort of blows up his experiment on to a macro level. So you can see in this experiment, what you're doing is you're taking a little mass just to make it random, just like air hockey. You're hitting pennies down at unknown masses, right? So you should not be able to see them, and you're counting how many times those pennies hit those masses, and you'd be able to measure the diameter of this when you hit those masses. So when I did this experiment, this is what I did. I hit 100 pennies down the lane, and I was able to calculate it using that equation there. And I was also able to calculate the percent error because those masses were 5 centimeters long, and there was 3 of them. So I used that equation right there, and if you want and more detailed, you can watch that video that was posted, that I've also posted. So you can see here, I shot 100 shots. Now, I stopped and calculated at certain intervals, at 1, 5, 20, 50, and then 100. Like I kept moving on. I didn't start over. You can see here what happened. Let's answer this first question based on this. So how did the number of shots affect the percent error of the calculated diameter? We can see that the percent error goes down. If I took one shot, I hit it. Well, based on the information I have, well, I'm close to 200% off, right? Um, and so this is sort of like, just think about that first shot. That first shot tells us a lot of information. If you completely miss and it goes through, well, based on that data, you don't know if anything's there to even hit, right? If you, let's just say you hit it once and it bounces back. Well, based on that data, you don't even know if the penny can make it all the way through. So that tells you a lot of information. Now, a second shot is going to give you a little bit more information. So at 2 shots, if you hit it once, or if you and it goes through once, then you know certain things. You know that it can go through and it can hit. So every shot is going to give you a little bit more information. That's why we did 100 shots. You can see at 100 shots, I was fairly accurate. I measured it, calculate was out 5.1 centimeters, only 2% off. Now, why was a person launching the penny supposed to be unable to see the masses? How does this recreate Rutherford's gold foil experiment? I'll give you a little hint there. Can you see atoms with your eyes? Well, you can't. It's because the wavelength of light is too long to really interact with it. You can't get a microscope small enough to see it. Yes, there are electron microscopes, but that's different. That does this same thing. It's bouncing electrons off of atoms and being able to like see them. But so the idea behind this is that you can't see atoms. Rutherford couldn't see those atoms. He wasn't aiming at anything. He just launched these alpha ray particles at it and was able to see how many reflected, how many bounced. Now, the question is, would the size of the coin used affect the number of hits? How would using a dime affect the number of hits? How would using a quarter affect the number of hits? Explain your answer. So, well, if a dime's smaller, there's a smaller likelihood of it hitting the masses. If you use a larger coin, there's a larger chance that it's going to hit those masses. And that's just because, and if you think about looking at the track, if you used a giant coin, it's probably going to hit, and it's because it has an actual depth to it. We're not actually, we're not measuring, you're not shooting just point particles at it. It does have some width to it that would affect it. And explain how Ernest Rutherford's gold foil experiment is similar to echolocation. So with echolocation, you're not really seeing anything. You're just bouncing sound off and being able to respond to that. It's just a different stimuli, being able to react to it. That's what the gold foil experiment was. All right, so then we move on to Niels Bohr. Now, Niels Bohr introduced the planetary model in 1913, and he advanced the theory that electrons traveled in orbits around the nucleus, and the number of electrons in the outer orbitals determine the atomic atom's chemical properties. So now we're getting into like chemistry here. So he was looking at the outside of it, and he was like, he know that the electrons go into these like orbitals. Now, then we get to Erwin Schrödinger, and he introduced the quantum model in 1926. Now, he used mathematical equations to describe the likelihood of finding an electron in a certain position. He worked a lot with quantum theory, and you've probably heard of Schrödinger's cat, right? So that's a famous thought experiment just to show how weird things can get at that quantum level. So this is the atomic theory, just based on observations and what we think of the atom. And the quantum model is what we're operating on now, but we're still discovering things new all the time. So this is how we, look at like atoms, right? So you've probably already looked at the atom. So we know that the nucleus is the center of the atom. It contains the protons and neutrons, right? Those nucleons. The electron cloud is the area surrounding the nucleus where electrons are found. The proton is the positively charged particle in the nucleus. The neutron is the neutral particle in the nucleus. And remember, neutral isn't a charge, right? It's just the absence of charge. Now, the electron is the negatively charged particle located in the electron cloud. So you've probably already learned this before. So now let's answer this question. Are you really you? So if you look at this is a thought experiment, the ship of Theseus, right? It's a thought experiment that raises the question of whether an object has all of its components replaced, remains fundamentally the same objects. So if you think, the idea is that Theseus goes on this trip, and and he replaces the parts of his boat, at every port, and then when he gets back, he's replaced every single part of that ship. Is it still the same ship? And if not, when did it cease to become that ship? Same thing with an axe. So, like if you're chopping wood, and then the handle breaks, and you replace the handle, is it still the same axe? And then if you're chopping that axe, and then the blade breaks, and you replace the blade, is it still the same axe? Now, the reason why I say this is because our atoms are constantly being cycled out, and every about 7 years, almost all of our atoms are replaced. Like cells are constantly taking in nutrients, they're expelling nutrients as waste, and it's constantly replacing that. So at what point do you cease to become you and become a different person? It's just an interesting thought experiment to have. Same thing with like thinking about how old you are. So if you look at the atoms of a newborn baby and the atoms of the oldest person alive, those atoms are going to be about the same age, and it's because in this height, a lot of height, most of hydrogen was created, or like all of hydrogen was basically created at the Big Bang. But the heavier elements, those are created in collapsing stars. So whatever star was here before, basically all atoms around this vicinity of space, like what we're made out of, the Earth, are about the same age. So just being able to say, well, how old are you? Well, that's just another interesting thought experiment to have, that the atoms are about the same age. So these are the origins of all of the atoms. Like you can see, some of them were Big Bang. All of hydrogen was a lot of helium, some lithium, but most of them came from stars going nova or supernova. All right, so if we look at this is simulation, this is just a quick little simulation that just reinforces these ideas of what, where the proton goes, neutron goes, where the electron goes, what they do. So if you look there, you add a proton and answer the question, where in the atom does it go? It goes to the nucleus. What happened to the mass number? The mass number should increase. What happened to the charge of the atom when the proton was added, right? So the charge should have went up one. The neutron, you can, so you do that for the neutron and the electron. So then you answer these questions. Well, explain what happened to or when you added the proton, what happened to the element, right? So the element is going to change. So what parts of the atoms affect the mass number? it's going to be the proton and the neutron. What part or parts of the atom affect the charge? What's going to be proton and electron? The proton increases the charge one, the electron decreases the charge one. And what part of the atom affects the element? That's going to be the proton. The proton is what affects that element, determines what the element is. So then what you have to do is you reset the simulation, make sure the box still checked as shown. Use the simulator to build each element in the table so it's stable and a neutral atom. So it's not an ion. So you can see here, explain what the mass number is. So the mass number is the number of nucleons in the center in the nucleus, right? So the number of protons plus neutrons. Then if we look at this conclusion, like protons have the same charge and are located in the same location as the atom. Similar charges repel. Explain how protons stay close together in the same location if the electromagnetic force is repelling them away from each other. So the answer is because of that strong force. Like, yes, those protons are trying to get away from each other, but the strong force, remember, it's like hundreds of times stronger than the electromagnetic force. And that's what holds the nucleus of an atom together. So it's going to be much larger. That's why they can be in the same place of the atom. So similar to that, if we look at this graph to the right, you can see here the x-axis represents the number of protons. The y-axis represents the number of neutrons. The line is where the number of protons equal neutrons. The dots are stable atoms that exist. So what can be said about the relationship between protons, neutrons, and the stability of an atom? Explain your answer. Well, if we look at this, we'll notice all of those stable atoms are going to be to the left of that. So that means they have more neutrons than protons. And that's because of that strong force. Yeah, you're going to add a bunch more protons. Well, those protons with electromagnetic force are going to be repelling away from each other. Neutrons need to be there to stabilize that atoms. And as those heavier elements go, it's not so much shown too much in this simulation because you notice down there at the bottom, you can't have the same number, sometimes less. In the case of hydrogen, you don't even need a neutron. But as you get heavier elements, those neutrons need to be there to stabilize that atom because of that strong force. So now let's go over how to identify an atom. So the atomic number identifies the element. It is the number of protons. So that's that bottom number there. The mass number is the number of protons plus the number of neutrons. And you can see that it's that top number there. Now the charge is the overall charge of the atom, and that's that top right. That just tells you what's the balance between protons and electrons. So an ion is an atom with a net charge due to loss or gain of electrons. And an isotope has the same number of protons, different number of neutrons. It's the same element though. So let's take a look at this one, right? So how many protons does the following atom have? Well, that's the atomic number. So it's going to have 11. How many neutrons does the following atom have? Well, it's going to have 12 because you take 23 minus 11. What is the net charge of the following atom? Well, this one's a little bit tricky because that positive 1 tells us I have one more proton than electron, and I know I have 11 protons. So if I have one more proton than electron, that must means I have 10 electrons. And all I have to do is take the atomic number minus the charge. That's how you get the number of electrons. So to determine the number of protons is just the atomic number. That's what determines the element. The number of neutrons is calculated by taking the mass number and subtracting the atomic number. Now, the number of electrons is calculated by taking the atomic number and subtracting the charge. So this is how you can find that. So let's take a look at another one, but this one has a negative charge, right? So the atomic number is going to be 35. The mass number is 79. How many protons does this atom have? That's just the atomic number. It has 35 protons. How many neutrons does the following? So I take the mass number, subtract the atomic number. 79 minus 35 is 44 neutrons. What's the net charge of the following atom? So that's going to be -1. So that tells me I have one more or one less electron, or sorry, one more electron than I do proton. So I take 35 minus a -1 and I get 36 electrons. So now let's talk about isotopes, right? So we learned about isotopes. It has the same number of protons but different number of neutrons. So if we look at carbon, carbon 12 has, all of carbon has 6 protons. That's what makes it carbon. Now, carbon 12 has 6 neutrons. Carbon-13 has 7 neutrons, carbon-14 has 8 neutrons, but they all have 6 protons. That's what makes it carbon. These are different isotopes. So you can see that, this is how some isotopes are broken down. Silver is about half and half, silver 109, silver 107. Chlorine's about, 3/4 to 1/4. Chlorine 35, chlorine 37. Carbon, most of it's carbon-12, some of it's carbon-13, and a small fraction is a radioactive carbon-14. You might have heard that in carbon 14 dating or carbon dating. And mercury is kind of all over the place. So this is the last question, right? How much do we really know about what the universe is made out of, right? So most of the atoms in the universe are hydrogen atoms, around 73%. And the majority of those atoms in the universe are just free floating hydrogen atoms in between galaxies. Now, some mass is gas. Some mass is gas in between stars inside galaxies. Most of those gases are hydrogen, but only about 7% of the atoms are stars, like you, me, planets, moons. So only 7% of that is going to be that. Now, this is just the atoms, right? Now, there is a problem, though, and that was dark matter. So in 1933, this astronomer named Fritz Zwicky, he was looking at different, these galaxies, and he said, well, based on their spin, galaxies shouldn't exist. There's not enough mass there to hold them together. Stars should be flying off. And when we started looking at galaxies, this was a common phenomenon, and it was confirmed in 1970 that the mass of a typical galaxy like Milky Way was only 10% of what needed for the galaxy to exist. But galaxies do exist. There's this unseen thing that is causing this extra gravity. That is what has been called dark matter, right? It's this something is causing this gravity that holds these galaxies together, right? But then there was another huge problem. Now in the 1990s, uh, astronomers discovered that galaxies were speeding up as they were moving away from each other, right? So and some of them are going to be traveling faster than the speed of light away from us. Now, they're not actually going faster than the speed of light, but what's happening is space in between those galaxies is expanding. There's more space, right? And the more space there is, the more it expands, and it's faster. It's increasing, right? So we call this something dark energy, some sort of an energy. It's like this pressure in the vacuum of space that's accelerating all gravities away from each other. So yeah, this is another thing that was discovered. So if you look at all of what we know, all the energy, all the matter in the universe, about 72% of it is dark energy, something that we just don't know. And dark matter makes up 23% of the universe. We have no idea what 95% of the universe is, right? So this is why I always say there's too much unknown in the universe to take a break from learning. So now most of the regular matter that we think of from the periodic table is just free-floating hydrogen atoms in space. So only 4% of everything that we know in the universe is those free-floating uh, hydrogen atoms. Now, 0.5% of the universe is stars. So if you look up at the sky, half of it is stars, but only 0.03% of the universe is heavy elements. So that's like you, me, planets, moons, like just what we think of as normal matter is actually really rare in terms of the universe, right? So that's why I always say this, and I'll end on this note. There's too much unknown in the universe to take a break from learning. Get out there and question everything.